Alright, so looking at 5 and 6 on your homework, it says for each problem, find f inverse prime of x. So you had a few ways you could go about doing that. One way you could do that is to simply find the derivative and do your inverse using our formula like that. So you could take the original function, you could flip x and y, so you get x equals, and let's turn off annotates. So you get x equals, and you have the square root of 2y plus 5, and then you could take your derivative of this, so you get 1 equals 1/2 2y plus 5 to the negative 1/2 times derivative inside, which is 2 dy dx. And then you'd solve for dy dx. So your 2's and your 1/2 cancel. You get 1 over the square root of 2y plus 5. And then the reason they can get this back to x is because originally we said x was equal to the square root of 2y plus 5. So over this way, if you solve for y, y is going to be equal to x squared minus 5, all divided by 2. And then you could plug that back into your function and simplify. The other alternative would be to take the derivative of that from the very beginning. So its derivative would look something similar to this answer here. And again, plugging in, it would simplify. Now number 6, the cubic makes that a little bit trickier. So let's clear out that. So your f inverse, again, you could flip your x and y's. And then if you wanted, solve for your y and then find your derivative. So you could take the cube of each side. I think this way is actually easier even than the other way to see this. So I resolve for y. So that is my inverse. So my inverse is negative 1/5 x cubed. And then negative 2/5 over another negative makes it a positive 2/5. So if you do your inverse and don't find the derivative of the inverse and you actually solve for your y value, and then you take the derivative of that, you get negative 3 x squared all over 5. And the 2/5 cancels out. And you could have done the same thing with number 5. Again, I was just kind of showing you the two different methods. But if you want to see 5 that way, also it's going to look very similar to this. So again, you would have had x equals the square root of 2y plus 5. So x squared minus 5 over 2 equals y. And that's your y inverse. So your y inverse prime with respect to x gave you derivative of that, which again, constants at the end, Derivative of x squared is 2x, but it's over 2. So those cancel, and you can see your x. So again, multiple ways of doing it. You can, and that's why we have 3 methods to manipulate, each one getting you down to a different type of solution set, but all of the solution sets represent the same thing. Yes.
Can I get you to do any of the 7, 8, 9, or 10? Doesn't matter to me.
To do like 7, 8, 9, or 10? Sure. We'll just start with 7, and then if you guys still need to see 8, 9, or 10, we can do that too. Let me insert a blank page. There you go. Alright, so looking at number 7, we have f of x equals x to the 5th plus 2x plus 5. And we're given a equals 5. And we're looking for f inverse of the derivative at a. So since we're looking for the inverse derivative at a, that tells me, according to my one formula, that I could find 1 over f prime of f inverse a, which means I need to know what x value on the original will equal this a value, because this is the a of the inverse, which makes it the y of the original. So that's kind of like saying 5 equals x to the 5th minus 2x minus 5. Solve for x. So if I added this 5 over, my 5's end up canceling, and I get 0 equals x to the 5th minus 2x. I can factor out an x, and I get x to the 4th minus 2. So my roots are x equals... What?
B is x to the 5th plus 2x.
So I copied down the problem, sorry. So this is a plus.
No, you're good. Sorry to interrupt you.
No, you're okay. I didn't realize I wrote a minus and it was a positive. And now I feel all messy, so I gotta start back over. It's not gonna change anything, but I don't like it being on. So x to the 5th plus 2x plus 5. But I still have 5 equals x to the 5th plus 2x plus 5. Subtracting my 5 from both sides. You have 0 equals x to the 5th plus 2x. Factor out your x. So you have x factored out, x to the 4th plus 2. So one of our roots is x equals 0. The other set of roots is x to the 4th equals negative 2. We know that that can't happen because those would be i's. So we kind of toss that out. So that means the point on my equation from the original is 0, 5. So that means on my inverse that it is f prime inverse of 5, because it asked me for a. So in this case, a is 5. equals 1 over all of this. But now my f inverse of 5 gives me 0. So this is 1 over f prime of 0. So I need f prime and plugging in 0, I get 2. Okay? Do I need to see 8, 9, or 10, or does that kind of make sense and we could work our way backwards on 8, 9, and 10 using that same method? So again, this is kind of using method number 1, where you are using your inverses and you're plugging into the derivative of the original, the x value of the original. So you're given the y of the original, so you plug in the x. Okay?
If there was more than one answer, you know, we threw out the
roots.
Imaginary. Right. If there was more than one, would there be more than one answer?
Yes. However, I know that there cannot be more than one, and that's a good question. And the reason there cannot be more than one, because in order for a function to have an inverse, for every x there is only one y, and for every y there is only one x, because in order for functions to be inverses, they have to be 1-to-1 to almost eliminate the problem that you're asking me about. Does that make sense? That was hard to explain.
No, it makes sense. So basically that will never happen.
Yeah, because by the very, very definition of an inverse, they have to be 1-to-1. So the minute they're 1-to-1, that duplicate answer can't happen. You're welcome. Okay, and then the rest of the worksheet was just reviewing your trig and your unit circle. So I've been reiterating how important it is to know your unit circle, how trig is coming back, and hopefully you took some time, you reviewed your unit circle. Hopefully doing those practice problems really helped you with reviewing your unit circle, and has allowed you to just feel more comfortable with the trig. Because what we're going to do today is actually find the formulas for the inverse trig derivatives. And we're going to work through finding the inverse by actually using trig to find the derivatives in general. And then I'm going to give you the formulas to memorize. But the reason I do it in general the very, very first time with this example 3 is because if you would forget one of your formulas on a test, or you're just totally bogged down, then you can actually find the inverse using one of the 3 methods we've done before. And for this one, I'm going to use the implicit method, so we're going to do method 2. But the idea is that you have so much knowledge about finding inverses that you actually don't need to memorize the formulas if you got to a point where that was an issue. So let's pick up with this y equals, and we have y equals sine inverse of x. And the problem is we don't know how to take the derivative of the inverse sine yet. So what we're going to do is almost apply what you were doing with the trig problems. We're going to get rid of the inverse by taking the sine of those sides. So if you recall from trig, if you take the sine of sine inverse, then because they're inverses of each other, they cancel each other. So this problem ends up becoming sine y equals x. And now this is something we can take our derivative of. And by definition, we're taking the derivative of the inverse sine because we've essentially flipped the x and y's of the original sine. So the derivative of sine is cosine. Our variable's y, so you have to take the derivative of the inside of that. So the derivative of y is dy dx. The derivative of x is 1. And then we know for implicit, we always solve for dy dx. So we get dy dx equals 1 over cosine y. So the inverse derivative of sine x is 1 over cosine y, but we don't like to have y's in our answers. So we could replace that y with a y from up above, which is sine inverse x. So at least now my derivative is with respect to x. So dy dx is 1 over cosine y, or 1 over cosine sine inverse x. And now let's think about triangle trig, right? So way back up here, we said that x was equal to sine y, or we had the idea that y equals sine inverse is equal to x. So we know that that's kind of the same as saying if I had a triangle and we'll put theta in the corner. And of course, this is a right triangle because trig is always right triangles. This is kind of like saying, all right, the sine of y is equal to x over 1. So y is kind of like my theta. X is my opposite, and 1 is my hypotenuse. So by Pythagorean theorem, we have the square root of 1 minus x squared, because it's hypotenuse squared minus length squared. So that's my adjacent side. So this is why we went back and did all of those trig problems with the unit circle. We can now say that sine inverse x is theta, or y in this case. Therefore, the cosine of y, which is adjacent over hypotenuse, could become 1 over the square root of 1 minus x squared. All over 1, but we don't need to write that again. Where x squared represents represents the length of the opposite, 1 is the hypotenuse, and x goes all the way back to the beginning where it's what's inside your inverse sine. You're going to see why that's important in a minute here. So this x matches up to the x inside the original. So, by definition, the derivative of sine inverse x is 1 over the square root of 1 minus x squared. This is, or does, represent the derivative of sine inverse x.
Where does the cosine go there?
I use SOHCAHTOA to replace cosine y, because y is really my theta, with adjacent over hypotenuse. So, like, if it was the cosine of 60, you would replace it with its trig value from the unit circle. In this case, since we don't know it's in general, you're replacing it with the triangle trig adjacent over hypotenuse. So, like, technically, I could do all my SOHCAHTOA values. Like, sine y is equal to x. Cosine y is equal to square root 1 minus x squared. And tan y would be equal to x over square root 1 minus x squared. Just by SOHCAHTOA. Are we good? What's funny is those alerts pop up, but I have it set to do not disturb. Okay, so in general, we have the following trig derivative formulas. Now, the difference from the example I just gave you is that these have a u instead of an x, because that u could be a function. So, like, you might find sine inverse of x squared, and the derivative of x squared is 2x. So that's where the u prime is coming to in the numerator. In the case of the problem we just did, the derivative of x was 1. So when you took the sine inverse, my u was x.
The following students please come to the office: Hannah Miller, Christian Myers, Hannah West, and Luca Tomasetti. Please come to the office.
So good.
Okay, so again, just like in the previous example, arcsine is the same as sine inverse. So the sine of arcsine or the sine of sine inverse are whatever your angle is. So if my angle is something other than x, then it would be that value as well. And again, that all comes down to the fact that sine and arcsine are inverses of each other. So by definition of an inverse, function composition says if you compose two inverses of each other, they will equal the identity, which is x. And we know that sine and cosine and tangent and all them are not one-to-one, which is why their domains are restricted for inverse derivatives. Okay, so find the derivative of f of t equals sine inverse t squared. So what I like to do is say, okay, my u value is t squared. So u prime is 2t. But in the formula, I also need u squared. So what I like to do is identify my u, find the derivative, and find its squared value. And then simply plug in. So the derivative of f with respect to t of sine inverse t squared is u prime over the square root of 1 minus u squared, which in this case is t to the fourth. And again, if you needed to see that in terms of a triangle, this is kind of like your theta. So the side opposite theta is that t squared. Your hypotenuse is 1. So again, we know that this would be 1 squared minus t squared squared, which is t to the fourth. So you can see how you get that cosine y down in the denominator again. But now, because we're finding the derivative, you have to take into account the derivative of your original theta, and that is where that 2t comes into play. So this blue would represent the original triangle. Okay, example number 5. Find the derivative of the inverse tangent. So once again, what I like to do is identify my u value. So in this case, my u value is the square root of x minus 1. Find your derivative of that. So that's 1/2 x minus 1 to the negative 1/2. Derivative of x is 1. And then u squared is not needed for the tangent problem. Actually, yeah, it is. Sorry. It's just not in our square root for our tangent. So a square root squared becomes x minus 1. So dy dx is u prime, which in this case is 1 over 2 square roots of x minus 1, all over And for tangent, it is 1 plus u squared. So 1 plus x minus 1, these ones cancel. We know it's a no-no to have a fraction in a fraction. So we're going to multiply by 1 over x to get it out of the denominator. So we get 1 over 2x square root x minus 1. Okay, find the derivative of y equals arctan. And apparently I had a brain boo-boo and put equals y twice. So, once again, we need to identify our u value, find its derivative, find its square. Now this is where you have to be careful. 3x squared is not 3x squared. It becomes 9x squared because both the 3 and the x get squared. And a lot of times when you have those types of problems, people forget to square the coefficient. They only square the variable. So once again, our formula says dy dx equals u prime, which is 3 over 1 plus u squared, which is 9x squared. This cannot be simplified. You cannot cancel the 3's. You cannot add the 1. Your derivative of arctan 3x is 3 over 1 plus 9x squared. If they gave you x values or y values, you would simply plug them in respectively. Okay, going back to just our trig days, there are a couple of formulas that help us every once in a while. So all I did was kind of try to give you an idea of how you could do these on a graphing calculator if you needed them. So these are just our trig identities for inverses, being able to use the calculator to find them. So what I had planned is that I know we're still kind of struggling with the inverse derivatives that are non-trig, but at the same time, we still need to, have an understanding of the trig ones. So in those packets I gave you, there are 2 sets of worksheets that follow today's notes. They are both labeled 3.8. So what you're doing for tomorrow is the 3.8 derivatives of inverse homework and the 3.8, and it's called homework inverse trig and derivatives. So you have the remainder of class time, which is a good bit of time to work on these. I will gladly help you or walk you through any of the problems if you're struggling, to help give you a better understanding for any of those problems. So I'm going to leave that Zoom connected, and if you get stuck, I will work through any of the problems or give you hints to sort of help you along.